Deep in the cosmic ocean lies a void so vast it defies belief, an emptiness so profound it challenges everything we think we know about the universe. It's a place where galaxies are strangers, scattered across an endless silent darkness. This is the Boötes void, a colossal hole in the fabric of space, a silent mystery hiding in the shadows of the universe's grand design. Discovered in the early 1980s, it shocked scientists. How could the universe have such an enormous region so completely devoid of matter? Like a cosmic black hole without gravity, it stretches over 1 billion light-years across. An enormous silent witness to the universe's most profound secret. Even in the vastness of creation, there are spaces so empty they seem almost otherworldly. What lurks in this hollow silence? Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. The universe is an expansive, ever-evolving tapestry woven from countless galaxies, shimmering stars, swirling nebulae, and mysterious dark matter. It's a cosmic masterpiece that stretches beyond the bounds of human imagination, governed by the laws of physics and shaped over billions of years. At its heart, the universe is a vast, dark void punctuated by luminous islands, galaxies that cluster together, separated by immense stretches of nearly empty space. On the grandest scales, the universe reveals a mind-boggling web-like structure. Galaxies are not randomly scattered. Instead, they form intricate patterns of filaments, walls, and nodes. These filaments are like cosmic highways connecting dense clusters of galaxies, forming what astronomers call the large-scale structure of the cosmos. Between these filaments lie enormous voids, regions of seemingly nothingness, where few galaxies exist and the space is eerily silent. The Boötes void is a prime example of such an enormous empty region. Spanning over 1 billion light-years across, it is often called the biggest hole in the universe. This vast cavern of emptiness challenges our understanding of cosmic formation, raising questions about what processes might have created such a colossal gap. These voids are not static. They evolve as the universe expands, pulling galaxies apart and creating more space for the cosmic web to stretch. Scientists have come to see the universe as a three-dimensional lattice, galaxies and matter forming a giant interconnected structure that extends across the cosmos. It's an astonishingly intricate system, where regions of high density dance alongside vast shadowy voids. The universe's architecture tells a story of gravity, dark energy, and the mysterious forces that have shaped everything from the tiniest particles to the grandest galactic superclusters. To understand the universe's vastness and structure, astronomers use a combination of observational techniques, advanced instruments, and analysis. These methods allow us to look back billions of years and across immense distances, revealing patterns such as galaxies, clusters, filaments, and voids like the Boötes void. The complexity of cosmic structures requires a multifaceted approach, integrating various observations and measurements. Telescope observations are fundamental. Ground-based telescopes, including optical observatories and radio dishes, capture visible and radio waves emitted by celestial objects. Space telescopes, like the Hubble Space Telescope, avoid atmospheric distortion, providing sharper images across ultraviolet to infrared wavelengths. These instruments have revealed distant galaxies and mapped cold hydrogen clouds. Observing different electromagnetic spectrum parts uncovers processes and structures that are faint, obscured, or energetic otherwise. Measuring cosmic distances is crucial to understanding scale. Direct measurement over billions of light-years is impossible, so astronomers rely on standard candles with known intrinsic brightness, such as type Ia supernovae. Comparing observed brightness with known luminosity yields distances via the inverse square law of light. Supernovae measurements help discover the universe's accelerated expansion, leading to the concept of dark energy. Another key method uses redshift, where light from receding galaxies shifts toward longer wavelengths. Spectroscopy measures this shift, which correlates with a galaxy's recessional velocity and distance, forming the basis of the Hubble law. This enables three-dimensional mapping of galaxies, Large surveys like the Sloan Digital Sky Survey, SDSS, catalogue millions of galaxies, recording their positions, redshifts, and properties. These data reveal the large-scale cosmic web of filaments, clusters, and enormous voids, regions containing fewer galaxies than surrounding areas. Voids such as the Boötes void extend hundreds of millions of light-years. These empty regions are vital for understanding cosmic evolution, showing how matter clumps under gravity over cosmic timescales. Their distribution and size help refine models related to dark matter, dark energy, and galaxy formation. The Cosmic Microwave Background, CMB, offers another insight into cosmic structure. Satellites like WMAP and Planck detect tiny temperature fluctuations in this faint afterglow of the Big Bang. These anisotropies contain information about the universe's composition, total density, and initial density fluctuations. Analysing the CMB helps determine the universe's age, about 13.8 billion years, and the relative amounts of dark matter, ordinary matter, and dark energy. The subtle variations in the CMB illuminate how tiny initial irregularities expanded into the vast web of galaxies and voids seen today. Gravitational effects, especially gravitational lensing, provide direct clues about the universe's mass distribution, including dark matter. Massive objects bend light from background galaxies, creating distorted or multiple images. By studying these distortions, astronomers map the dark matter that constitutes about 85% of the universe's matter. Galaxy motions, cluster dynamics, and lensing help reveal how mass, visible and unseen, shapes the structure of the cosmos. These measurements confirm that visible matter alone cannot account for observed gravitational effects, indicating dark matter provides the framework for galaxy formation and large-scale structures. Combining these techniques, multi-wavelength observations, redshift measurements, large surveys, CMB data, and gravitational lensing, enables the construction of detailed three-dimensional maps of the universe. These maps display positions and structures of billions of galaxies and clusters, as well as the distribution of cosmic voids like the Boötes void. This comprehensive understanding allows testing of cosmological models, refinement of parameters, and exploration of fundamental questions about the universe's origin, composition, and ultimate fate. Through precise measurements and innovative analysis, the faint light from space's depths becomes a profound window into the universe's vast, intricate architecture. The universe is a vast, intricate tapestry woven from a myriad of structures, each playing a vital role in shaping the grand cosmic landscape. At its most fundamental level, the universe is composed of galaxies, massive systems of stars, gas, dust, and dark matter, all bound together by gravity. These galaxies are the building blocks of the universe, ranging from tiny dwarf galaxies to colossal giants containing hundreds of billions of stars. Galaxies rarely hang out alone. Instead, they tend to cluster together, forming groups and clusters that can contain just a few stars to thousands of galaxies bound by gravity. These galaxy clusters are among the largest gravitationally bound structures in the universe and serve as the cosmic cities where galaxies mingle, interact, and sometimes collide, igniting spectacular star formation episodes or fueling active galactic nuclei. But galaxies don't cluster randomly. Instead, they are woven into an enormous interconnected network known as the cosmic web. This cosmic web is composed of long, thread-like structures called filaments, vast strands of dark matter and luminous matter that stretch across millions of light-years. These filaments are the highways of the universe, channeling matter and energy into clusters and forming the skeletal framework of the cosmos. Along these filaments, galaxies are often arranged in chains or ribbons, giving the universe its characteristic web-like appearance when viewed on the larger scales. Between these filaments lie enormous regions known as voids. Voids are vast, nearly empty spaces where galaxy density dramatically drops. Some voids are so expansive that they span hundreds of millions of light-years, containing only a handful of galaxies, if any at all. The Boötes void, which has earned the nickname the biggest hole in the universe, is one of the most famous examples. It measures approximately 65 million light-years across, and is starkly deficient in galaxies compared to surrounding regions. Its existence highlights how the universe's matter isn't evenly spread, but instead concentrated along filaments and in clusters, leaving large expanses of emptiness in between. Lining the edges of these voids and filling the filaments are galaxy groups and smaller clusters. These regions act as the nodes in the cosmic web, where matter densities are higher and galaxies are densely packed. The entire structure resembles a three-dimensional spiderweb, with filaments as the threads, clusters as the knots, and the vast voids as the gaps between them. Dark matter underpins much of this architecture. Although invisible, dark matter constitutes about 85% of the universe's total matter. Its gravity acts as the scaffolding upon which ordinary matter settles, guiding the formation of galaxies, clusters, and the immense filamentary structure. Without dark matter, the universe's structure would look very different and less organized. The interplay between these components, the galaxies, their clusters and groups, the filaments connecting them, and the enormous voids creates a dynamic, ever-evolving cosmos. Over billions of years, gravity has sculpted this complex web from an almost uniform early universe, amplifying tiny fluctuations in matter density. The result is a universe that is both incredibly rich in structure and profoundly mysterious, with vast regions of emptiness contrasting sharply against the dense conglomerates of matter. Understanding these components is essential to unraveling the story of the universe. From the birth of the first galaxies in tiny fluctuations to the grand cosmic web that stretches across the universe today, each piece fits into a bigger picture, a universe that's a colossal, interconnected, and ever-expanding masterpiece. The Boötes void stands as a testament to this complexity, an enormous gap reminding us that even in the universe's vastest spaces, there are still immense mysteries waiting to be uncovered. Understanding the large-scale structure of the universe is fundamental to unlocking the deepest secrets of cosmology, because it is like viewing the universe's blueprint, its grand architecture that reveals how everything came to be and how it continues to evolve. When astronomers map the vast cosmic web, they aren't just sketching pretty pictures, they're uncovering clues about the underlying physics that govern the cosmos. These structures, galaxy clusters, superclusters, filaments, walls, and vast voids are the fingerprints of cosmic history laid out across billions of light years. At the heart of this exploration is the recognition that the universe is far from uniform. On smaller scales, galaxies are sprinkled across space seemingly at random. But when we zoom out and examine the universe on scales larger than hundreds of millions of light years, patterns start to emerge. These patterns aren't accidental. They are the result of physical processes dating back to the universe's infancy, shortly after the Big Bang. Tiny quantum fluctuations in the early universe, amplified by cosmic inflation, served as the seeds from which all large-scale structure grew. Matter gradually clustered along the densest regions, forming the cosmic web we observe today. The distribution and shape of that web tell us about the mysterious components that make up our universe: dark matter, dark energy, and ordinary matter. For example, dark matter plays a crucial role in scaffolding the universe. Its gravitational pull pulls matter together to form the galactic and supergalactic structures we see. If dark matter behaved differently, or if the laws of gravity were different from our current understanding, the large-scale structures would look very different as well. By studying their arrangement, we directly test the theories that describe the universe's composition and the forces that shaped it. Void regions, like the Boötes void, are particularly revealing. These gigantic empty spaces, sometimes spanning hundreds of millions of light years, are like the negative space in a cosmic sculpture. Their presence and size challenge us to understand the distribution of matter and the influence of dark energy. Why do these voids exist? How did they grow? How do galaxies and matter behave at their edges? These questions aren't just about filling in gaps. They're about understanding the fundamental mechanisms that drive cosmic expansion and structure formation. Voids serve as natural laboratories for studying the universe's accelerated expansion and provide critical tests for cosmological models. Moreover, examining the large-scale structure helps to constrain the parameters of our cosmological models with greater precision. The detailed shape of the cosmic web, the abundance of galaxy clusters, and the properties of voids all feed into simulations that allow scientists to compare predictions with observations. Discrepancies can point to new physics, perhaps hinting at unknown particles or forces. Every new survey, be it through radio, optical, or X-ray telescopes, adds pieces to this cosmic puzzle, refining our understanding of the universe's past, present, and future. Finally, understanding large-scale structure bridges the gap between the very small and the very large. It connects quantum physics with relativity, from the minute fluctuations in the early universe to the enormous structures spanning billions of light years, recognizing that the universe's grand design encodes both the initial conditions of the Big Bang and the subsequent evolution driven by mysterious components like dark energy, transforms how we see ourselves in this cosmic scale. It echoes a profound realization that every galaxy, every void, and every filament is part of a vast interconnected story. A story that continues to unfold as we peer ever deeper into the universe's depths. Cosmic voids are nothing short of cosmic giants, dwarfing many of the structures that we often think of as the largest in the universe. To understand just how enormous they are, imagine stretching a piece of fabric so thin that a single grain of sand could cover its surface. Now picture that this fabric is the universe itself, and the giant empty patches, voids, are areas that are so expansive they defy ordinary comprehension. Take the Boötes void, for example. This colossal cavern in space spans roughly 150 to 200 million light-years across. That's more than enough space to fit several 100,000 Milky Way galaxies, each with their own billions of stars, planets, and cosmic dust. The sheer size dwarfs the realm of galaxy clusters, superclusters, and even filaments, the grand cosmic structures that stitch the universe into its web-like form. The galaxies and galaxy clusters tend to be concentrated along these filaments and walls, leaving the vast, nearly empty spaces in between as the cosmic voids. Compared to galaxy clusters, which might contain a few hundred or a few thousand galaxies packed together, voids look like nothingness on an almost incomprehensible scale. Galaxy clusters typically span a few million light-years at most, still massive, but nowhere near the size of the voids that swallow up hundreds of millions of light-years. When you think about superclusters, the most massive structures in the universe, they stretch across tens of millions of light-years, but even they are dwarfed by the scale of voids like Boötes. And what makes these voids even more significant isn't just their size, it's what their existence tells us about the universe's fundamental fabric. Void regions are almost entirely empty of matter. No bright galaxies, no stars, just a sparse sprinkling of isolated galaxies or tiny galaxy groups. In a way, they act as the universe's quiet, dark backdrops, emphasizing the contrast between the densely packed filaments and walls and these enormous pockets of emptiness. Understanding these vast empty spaces sheds light on the distribution, the evolution, and even the very nature of cosmic matter. The significance of cosmic voids reaches beyond just their size. They serve as cosmic laboratories for understanding the universe's history and its large-scale structure. Because they are so emptiest regions, they are less affected by the complex gravitational interactions that dominate galaxy clusters. This makes them cleaner environments for testing theories about dark matter, dark energy, and the overall shape and expansion of the universe. For example, studying how galaxies are distributed within the voids can help scientists comprehend how structures grew over cosmic time, influenced by forces such as gravity and the mysterious dark energy that drives inflation and expansion. Void regions are also key to understanding the large-scale uniformity of the universe. The existence of such massive, seemingly empty spaces supports the idea that the universe, on the largest scales, is remarkably homogeneous and isotropic. They act as the universe's vast cosmic voids of silence amidst the bustling activity of galaxy formation, helping cosmologists map out the evolution of cosmic structures and test the fundamental principles of cosmology. In a universe where galaxy clusters and celestial giants dominate our view, the cosmic voids remind us of the profound emptiness and immense scales that stretch between the luminous islands of stars and galaxies. They redefine what we mean by large and challenge our understanding of the universe's architecture. The Boötes void isn't just a big hole in space, it's a testament to the universe's grandeur, its intricate web of matter and emptiness, and the endless questions waiting to be answered about the cosmos we call home. Cosmic voids are enormous, almost invisible regions in the universe that contain very few, if any, galaxies. Imagine looking at the night sky and seeing clusters of luminous galaxies shining brightly amidst vast, empty patches. Those are the cosmic voids. These regions can stretch for hundreds of millions of light-years, making them some of the largest structures in the universe. Their presence might seem counterintuitive at first glance because we often think of the universe as densely packed with stars and galaxies. But in reality, cosmic voids are the silent, expansive gaps that reveal just how uneven and lumpy the universe's large-scale structure really is. The story of how we first discovered cosmic voids is a fascinating chapter in astronomical history. It dates back to the mid-20th century when astronomers began mapping the universe more systematically. Early galaxy surveys, such as the cataloguing efforts of astronomers like George Abel and Gerard de Vaucouleurs, started to reveal that galaxies were not randomly sprinkled throughout space, but instead grouped into clusters, superclusters, and long filaments. Amidst this cosmic web, there were noticeable regions where galaxies seemed conspicuously absent. These were the first hints of what we now recognize as voids. It was a combination of technological advancements and more comprehensive galactic surveys that made the discovery of cosmic voids possible. The advent of photographic plates and later digital sky surveys allowed astronomers to catalogue hundreds of thousands of galaxies. With these data in hand, they created three-dimensional maps of galaxy distributions, revealing the large-scale structure of the universe in extraordinary detail. It was in these maps that the vast empty regions began to stand out clearly, leading to their recognition as genuine cosmic features rather than mere observational artifacts. One of the first recognized cosmic voids was identified in the 1970s through detailed galaxy surveys. Known as the Boötes void, it surprised astronomers with its enormous size, approximately 150 million light-years across, making it one of the largest known voids at the time. The discovery of the Boötes void was akin to finding a giant hole in the fabric of the universe, a region almost devoid of galaxies surrounded by bustling galaxy clusters. The existence of such a void challenged existing cosmological theories and prompted scientists to rethink how matter clumps together over cosmic time. Thanks to ongoing surveys, including the famous Sloan Digital Sky Survey, our understanding of cosmic voids has grown exponentially. We now recognize that voids are not simply empty gaps, but dynamic regions that evolve over time and influence the movement of galaxies around their edges. They act as cosmic basins, where matter tends to flow away from the emptier areas toward the more densely populated regions, shaping the universe's large-scale structure. Cosmic voids serve as cosmic laboratories. They are not just empty spaces, but vibrant regions that carry vital clues about the universe's origins, the nature of dark matter, and the force of dark energy. They help us understand how structures grow and evolve, and why matter is distributed the way it is on the grandest scales imaginable. The discovery of these colossal voids was a milestone that transformed our view of the universe, revealing it to be a vast, intricate tapestry, woven with both luminous galaxies and silent, sprawling emptiness. Astronomers use various methods to identify, analyze, and understand cosmic voids, combining observational techniques, statistical tools, and computational models to explore these large empty regions in the universe. A primary approach involves large-scale galaxy surveys, which map the distribution of millions of galaxies across the sky and through cosmic time. Notable examples include the Sloan Digital Sky Survey, SDSS, and the 2DF Galaxy Redshift Survey, which create detailed three-dimensional maps based on redshift measurements. Redshift, caused by the universe's expansion, indicates a galaxy's distance by measuring how much its light's wavelength has stretched. By compiling redshift data, astronomers visualize the universe's large-scale structure, revealing dense clusters, filaments, and vast voids, regions with significantly fewer galaxies that can span hundreds of millions of light-years. In addition to cataloguing galaxy positions, scientists analyze the statistical properties of this structure using tools like the two-point correlation function. This measures the likelihood of finding galaxy pairs at different separations compared to a random distribution. Low correlations at large scales signal the presence of voids. The void probability function, VPF, further characterizes voids by measuring the likelihood of finding an empty volume within a certain scale, helping determine their sizes, shapes, and spatial arrangements. These statistical methods provide insights into the physics of cosmic structure formation. Deep redshift surveys allow researchers to observe voids at earlier cosmic times, revealing their evolution over billions of years. Comparing void properties across different epochs shows how they expand and merge as the universe matures. Studying this growth helps inform models of cosmic expansion and dark energy, which influence large-scale structures. Tracking void evolution tests theories about gravitational instability and dark matter's role in shaping the cosmic web. Gravitational lensing offers an indirect method to study voids. While strong lensing is associated with massive clusters, subtle lensing signals can be detected around underdense regions. Weak gravitational lensing measures slight distortions in background galaxy shapes caused by matter, including dark matter, within and around voids. This technique enables mapping the underlying mass distribution, confirming the underdensity of both luminous and dark matter, complementing optical galaxy surveys. The Cosmic Microwave Background (CMB) provides a background probe for signatures of large voids via the integrated Sachs-Wolf effect. When CMB photons pass through evolving gravitational potentials associated with voids, they experience energy shifts, either gaining or losing energy, leading to temperature fluctuations that correlate with void locations. Detecting these signals offers evidence of the size and influence of large voids, relevant in understanding cosmic acceleration and dark energy. Numerical simulations are crucial for understanding voids, as they recreate the universe's evolution based on physical principles and dark matter models. By inputting parameters like dark matter, dark energy, and initial density fluctuations, scientists generate virtual universes. Comparing these simulations with observations validates or refines theories about how voids form, grow, and affect their surroundings, including their role in the cosmic web and the impact of dark energy on their expansion. By integrating observational surveys, statistical analyses, lensing studies, CMB observations and simulations, astronomers develop a comprehensive understanding of cosmic voids. These methods help locate, characterize, and explore their properties, evolution, and significance within the universe's large-scale structure. Each technique provides unique insights into these vast empties, such as the Boötes void, contributing to our broader understanding of cosmic architecture and fundamental physics. Void regions like the Boötes void play a crucial role in shaping the universe's large-scale structure. Though they may seem like empty gaps, their influence extends far beyond mere emptiness. These vast, near voids act as cosmic laboratories, helping scientists understand how the universe develops over billions of years. To grasp how voids influence cosmic evolution, it's important to consider their place within the cosmic web. The universe isn't just a random collection of galaxies, it's organized into an intricate network of filaments, clusters, and voids. Imagine a three-dimensional spiderweb with dense nodes and sprawling empty regions. Galaxies tend to cluster along filaments and knots, leaving voids, like the Boötes void, remarkably sparse. But this sparseness isn't just empty space, it actively interacts with the universe's structure. Voids influence matter flow by guiding its movement over cosmic timescales. Gravity pulls matter from less dense regions toward denser areas, meaning galaxies and gas migrate out of voids into filaments and clusters. The underdensity within a void causes it to expand faster than denser regions, making voids grow larger and more emptier over time. This process effectively scoops out material from within voids, pushing matter outward toward denser structures and reinforcing the cosmic web's architecture. Voids also impact the evolution of dark matter and dark energy. Being almost devoid of matter, they serve as pristine environments for studying these mysterious components. The expansion rate within voids can differ from the overall universe, offering insights into dark energy's properties. Monitoring void growth helps scientists determine whether cosmic acceleration is uniform or varies regionally. Thus, voids act as natural laboratories to test ideas about the universe's fundamental forces. Beyond structure and dynamics, voids hold clues to the universe's origins. Their distribution and sizes reflect the primordial density fluctuations that emerged after the Big Bang. By examining these vast empty regions, scientists trace back to the universe's initial conditions and the tiny quantum fluctuations that eventually formed the cosmic web. The sizes, shapes, and arrangements of voids serve as a cosmic record of early-stage structure formation, revealing how the universe's initial seeds grew into the complex web of galaxies seen today. Voids also influence the propagation of light across the cosmos. When photons from distant galaxies pass through these empty regions, they experience less gravitational lensing compared to dense areas with massive clusters. This difference affects measurements of cosmic distances and the universe's expansion rate. Understanding voids allows astronomers to account for these effects, leading to more precise models of how the universe expands and evolves. In conclusion, voids like the Boötes void are more than empty space. They are active, dynamic regions vital to understanding the cosmos. They shape the universe's structure, influence its evolution, and provide windows into dark matter, dark energy, and the early universe. Far from being mere gaps, these vast regions hold the keys to unlocking fundamental cosmic mysteries, guiding scientists in deciphering the universe's past, present, and future. Word count 507. Among the colossal voids that have captured scientists' interest, several stand out due to their size and the insights they offer into the universe's vast, mysterious structure. These enormous regions of emptiness are like cosmic scars, reminding us how much space remains almost completely devoid of galaxies, stars, and matter. Their study is vital, as they serve as natural laboratories for understanding the forces shaping the universe. One of the best-known and most studied voids is the Boötes void, often called the Great Nothing. This immense void is roughly 1 billion light-years across and is located in the constellation Boötes. Discovered in the early 1970s, it was a game-changer. When astronomers mapped galaxy distributions there, they found an astonishing absence of galaxies, making it one of the largest known voids. The Boötes void's existence led to questions about how such an expansive, empty space could form amid the cosmic web, prompting deeper research into the influences of dark matter and dark energy on large-scale structures. Another notable example is the large void in the southern hemisphere sky. Similar in size to the Boötes void, it contains a sparse distribution of galaxies and galaxy groups. These enormous voids are not simply empty gaps, but complex regions that influence how galaxies move along their boundaries, guiding the flow of matter through gravitational pull. The interconnectedness of these voids and filaments demonstrates the intricate structure of the universe. The Sloan Great Wall is a massive galaxy filament, not a void, but it's bordered by enormous voids. This enormous structure exemplifies the universe's large-scale design, with voids filling the spaces between the giant filaments. Studying the arrangement of these structures helps scientists understand how the cosmic web evolved over billions of years, shaped by primordial fluctuations and the influence of dark energy. Beyond these well-known voids, scientists are continually discovering new ones through in-depth galaxy surveys. The KBC void, named after astronomers Kevin Koppen, Brent Tully and colleagues, is a large underdensity about 1 billion light-years across near our cosmic neighbourhood. Its existence raises questions about whether our local universe is unusually empty, which could affect measurements of the universe's expansion rate and the Hubble constant. Studying these voids involves more than cataloguing emptiness. It reveals the universe's history. The size, shape, and distribution of voids are clues that help refine models of cosmic evolution. They act as natural experiments, areas where the gravitational pull is minimal, allowing researchers to observe how the universe behaves without the influence of dense matter. Understanding these vast voids can shed light on dark energy, the mysterious force driving the universe's accelerated expansion. The growth and evolution of voids over cosmic time serve as indirect evidence of dark energy's effects on large-scale structure, offering insights into forces beyond direct observation. As telescopes and surveys grow more advanced, scientists are likely to find even more giant voids, enriching our picture of the universe's grand architecture. Each discovery highlights a fundamental truth. At the largest scales, the universe is a tapestry woven from both luminous matter and vast emptiness. The cosmos remains as mysterious as it is magnificent. Voids such as the Boötes void are fundamental to understanding the universe's large-scale structure and evolution. These enormous, underdense regions, spanning hundreds of millions of light-years, are not just empty spaces but serve as cosmic laboratories that reveal insights into the physics shaping our cosmos. Their importance arises from their unique environment, simplifying many variables and allowing astronomers to probe questions about dark matter, dark energy, gravity, and the universe's earliest moments. One reason voids are crucial is their extreme emptiness, which amplifies the effects of dark matter and dark energy by providing a relatively clean environment. Unlike dense galaxy clusters, where gravity is complex due to interactions among massive objects, voids experience minimal such influences. This simplicity makes deviations from expected behaviour like anomalies in galaxy distribution or expansion, easier to detect, making voids ideal for testing cosmological models. For example, modifications to gravity theories or alternative explanations for cosmic acceleration can be more clearly observed in voids, providing powerful constraints. Voids also serve as sensitive indicators of cosmic expansion. Their growth and shape evolution directly reflect the universe's expansion rate. By measuring the size and distribution of voids over cosmic time, scientists gain crucial data about dark energy's influence, the force driving accelerated expansion. Discrepancies between observed void properties and model predictions could suggest the need for revised theories or new physics. For instance, unexpectedly rapid growth of voids might indicate variations in dark energy's density or behavior, prompting re-evaluations of current cosmological paradigms. Additionally, voids provide insights into dark matter's distribution and behavior. Dark matter shapes galaxy formation and the cosmic web, but its influence in voids is minimized, enabling easier studies of its effects. Examining galaxies at void edges allows astronomers to compare observations with models predicting dark matter's clustering properties. These comparisons help refine our understanding of dark matter's nature and its role in structure formation. Void properties also serve as relics of the universe's infancy. Their large-scale patterns trace back to initial density fluctuations, from quantum perturbations during inflation, shortly after the Big Bang. The initial matter distribution, imprinted in the cosmic microwave background, laid the foundation for the cosmic web, with voids marking regions of low initial density. Studying things like the Boötes void helps cosmologists reconstruct early universe conditions, shedding light on processes from billions of years ago. Over cosmic time, voids evolve due to ongoing expansion and gravitational effects. They tend to become larger and emptier over time, acting as cosmic bubbles. Monitoring their growth provides a direct measure of how fast the universe is expanding. If voids expand faster than models predict, it may indicate new physics beyond the standard model, such as modifications to dark energy or gravity theories. Finally, voids offer a unique testing ground for alternative theories of gravity. Many modified gravity models predict different behaviors in low-density regions compared to high-density environments. Studying void dynamics, galaxy distributions, and gravitational lensing within these regions allows scientists to evaluate whether Einstein's general relativity accurately describes gravity on cosmic scales, or whether alternative theories are necessary. In some, cosmic voids like the Boötes void are more than empty spaces. They are natural experiments that help decode the universe's deepest mysteries. Their size, shape, growth, and internal dynamics provide invaluable clues to understanding the origin, composition, and fate of our universe, making them essential tools for cosmologists seeking to uncover the fundamental laws governing everything from particles to the cosmic web. The discovery of the Boötes void is a story that highlights the evolution of astronomical observation and our understanding of the universe's vastness. It was identified during a time when astronomers were really beginning to map the large-scale structure of the cosmos, in the late 1960s, a period marked by rapid advancements in telescope technology and galaxy surveys. Back then, astronomers had already begun to compile sizable catalogues of galaxies, meticulously measuring their positions and redshifts to understand how galaxies are distributed across space. The challenge was immense. The universe is so expansive that ordinary telescopes couldn't easily detect all distant galaxies, especially the faint and far-flung ones. But with the emergence of more powerful telescopes and more systematic surveys, scientists could map larger areas of the sky with unprecedented detail. The breakthrough came with the work of two American astronomers, Robert Kirshner and colleagues, who were part of a team conducting extensive galaxy redshift surveys. They used the then newly operational Hale telescope at Mount Palomar and other observatories to measure the distances to thousands of galaxies, constructing a three-dimensional map of their distribution. This map revealed an intricate cosmic web, a vast network of filaments and clusters separated by enormous empty regions, voids. In 1980, the region known as the Boötes void was officially identified and documented. It was during a large galaxy redshift survey aimed at understanding the large-scale structure that astronomers noted a startling anomaly, a huge, roughly spherical region largely devoid of galaxies. This was unlike anything observed before, a genuinely empty space spanning about 150 million light-years across. The scale was mind-boggling. Imagine a volume of space so enormous that it encompasses several galaxy superclusters, yet is almost entirely devoid of galaxies, stars, or other luminous matter. The discovery was somewhat serendipitous. As astronomers plotted their data, they noticed an area where the usual density of galaxies plummeted. Initially, some skeptics wondered if it was just an observational artifact, a place where the telescopes couldn't look deep enough or where bright stars in the foreground obscured faint galaxies. But repeated observations confirmed the void's existence and space's emptiness, making it one of the most remarkable features of our universe. This finding was groundbreaking because it challenged the previously held notion that matter was evenly distributed at large scales. Instead, it revealed that the universe, while overall homogeneous and isotropic on very large scales, contains vast empty patches, like the Boötes void, that stretch the imagination and compel us to reconsider the processes that shape the cosmos. The discovery of the Boötes void is a perfect example of how technological advances and systematic surveying can unveil the universe's hidden grandeur, revealing structures that push the limits of human imagination and fuel ongoing questions about the nature of dark matter, dark energy, and the very fabric of space itself. It remains a symbol of the universe's incredible scale and the enduring curiosity that drives astronomers to explore the unknown. Nestled within the cosmic web is a staggering emptiness known as the Boötes void. Imagine a vast, nearly empty bubble stretching over 180 million light-years across, a size so immense that it is difficult to truly grasp. For comparison, our entire Milky Way galaxy, with its sprawling arms and billions of stars, is a mere speck next to this cosmic vacuum. The sheer scale of the Boötes void dwarfs many of the structures scientists have observed, making it one of the most striking examples of a cosmic void, a region with a profoundly lower density of galaxies than the surrounding universe. At its core, the Boötes void is a region remarkably deficient in galaxies, containing perhaps only a few dozen small galaxies, where we might expect thousands or even millions in a comparable volume. This stark emptiness contributes to its reputation as one of the largest known voids in the universe. Its boundaries are not sharply defined like the walls of a box. Instead, they gradually transition into denser regions teeming with galaxies, clusters, and filaments that make up the cosmic web. To a casual observer, it appears as a colossal, dark hollow embedded within an intricate tapestry of luminous matter. The physical characteristics of the Boötes void extend beyond just its size. Its shape, while roughly spherical, shows signs of irregularity, almost as if cosmic upheavals or initial density fluctuations caused this region to expand differently over cosmic time. The void's low-density environment means it contains very few of the matter, gas, dust, dark matter, that typically clings together under gravity to form galaxies and stars. This scarcity of matter results in an environment with almost negligible gravitational pull, allowing it to expand and grow even more over billions of years. Inside the void, the matter density is astonishingly low, less than 10% of the average density of the universe. This scarcity means that dark matter, which makes up a substantial part of the universe's overall mass, is also significantly underrepresented here. As a result, the region exerts minimal gravitational influence on the surrounding structures. Because of this, galaxies that are near the edges of the void tend to be pushed outward, and the void itself appears to be expanding faster than average regions of the universe. The characteristics of the Boötes void aren't just confined to its size and density. The void offers unique insights into the universe's large-scale structure and evolution. The sparse environment inside it makes it an excellent laboratory for studying the properties of dark energy and dark matter, components that govern cosmic expansion but are otherwise nearly invisible. The emptiness reduces the noise created by gravitational interactions from nearby galaxies, allowing astronomers to analyze how these mysterious forces operate in relative isolation. While the Boötes void might seem like a mere absence, its existence is a testament to the dynamic processes that sculpted our universe. It reminds us that the cosmos is not a uniform expanse, but a complex layered structure with regions of intense activity and vast silent emptiness, each playing a crucial role in the grand story of cosmic evolution. This enormous whole invites us to ponder how matter clumped together to form the galaxies we see today, and what the emptiness reveals about the forces at work shaping the universe's future. The size of the Boötes void was determined through an intricate process that combined meticulous observations and sophisticated analysis. Astronomers first began mapping the universe by cataloguing the positions and distances of countless galaxies, using extensive galaxy surveys that charted millions of celestial objects across vast stretches of space. These surveys relied heavily on measuring the redshift of galaxies, a phenomenon where light from distant galaxies shifts toward the red end of the spectrum because of the universe's expansion. By analysing these redshift measurements, scientists could infer how far away each galaxy was. When mapping out the known universe on a large scale, researchers noticed regions where galaxies appeared startlingly sparse. The Boötes void stood out as one of the most conspicuous empty patches, so vast and so noticeably devoid of galaxies that it captured the imagination of astronomers. However, simply noticing the void was not enough. Measuring its exact size required careful, systematic analysis. The process involved defining the boundaries of the void by examining the distribution of galaxies in three-dimensional space. Researchers used data from large-scale galaxy surveys such as the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey, which provided detailed maps of galaxy positions over extensive regions of the sky. By plotting these positions, astronomers could visualize the large-scale structure, the cosmic web, and identify continuous regions where galaxy density dropped dramatically. To validate the size measurement, scientists established a threshold for what constitutes the edge of the void. Typically, areas where galaxy density fell below a certain fraction of the average cosmic density. They then analysed the shape of the void, noting that its boundaries were not perfectly spherical but elongated and irregular, much like cosmic soap bubbles. The size estimates often reference the largest spherical approximation that could fit within the boundaries, providing a standardized metric for comparison. Further validation came through cross-checks across multiple independent surveys. When different datasets yielded consistent results, confidence in the measurements increased. Beyond purely galaxy-based methods, other techniques such as the study of Lyman alpha forests, which trace the distribution of hydrogen gas between galaxies, offered additional confirmation. These gas maps revealed similar large-scale underdensities, reinforcing that the void was a genuine structure rather than an artifact of observational bias. Cosmic microwave background observations also contributed indirectly. Although the CMB provides a snapshot of the universe when it was only about 400,000 years old, long before galaxies and voids fully formed, analyses of CMB anisotropies helped refine cosmological models. These models help predict the expected size and distribution of voids, which researchers compare against their observed measurements for consistency. To ensure their findings were robust, astronomers employed computer simulations mimicking large-scale structure formation under various cosmological models, run with parameters consistent with our understanding of dark energy and dark matter. These simulations generated virtual universes where voids of similar size naturally emerged. Comparing simulation results with actual observations allowed scientists to confirm that the size of the Boötes void was consistent with the predictions of current cosmological theories. Ultimately, by combining precise galaxy surveys, redshift measurements, gas observations, and computational modelling, scientists achieved a reliable and validated measurement of the Boötes void's enormous, truly mind-boggling size. It isn't just a statistical anomaly, it's a real cosmic feature that continues to serve as a critical testbed for understanding the universe's grand architecture. The Boötes void is notable not only for its size, but also for how it challenges our understanding of the universe's large-scale structure. While cosmic voids are common features in the cosmic web, vast regions with far fewer galaxies than average, the Boötes void is extraordinary, often called the Great Nothing due to its intense emptiness. Measuring about 150 million light-years across, the Boötes void is enormous. It contains only a tiny fraction of the galaxies expected in such a region. To grasp its scale, travelling at light speed would take over 1 billion years to cross it. As one of the largest known voids, its emptiness is staggering, with fewer than 100 galaxies, tiny islands amidst vast emptiness, where models predict thousands should exist. What makes the Boötes void particularly unique extends beyond its size and galaxy scarcity. Its discovery in the early 1980s fundamentally altered our view of cosmic structure. Prior to that, scientists believed matter was more evenly distributed, with large structures separated by voids. The existence of such an immense emptiness as the Boötes void showed that the gaps could be extremely dramatic, forcing astronomers to rethink galaxy distribution and the processes shaping the universe. Another intriguing feature is the arrangement of galaxies around the void. Its edges are like cosmic boundaries, lined with clusters and filaments of galaxies that seem to form a frame for this vast emptiness. Inside, the galaxies are isolated and sparse, suggesting the void isn't just a random gap but possibly the outcome of complex cosmic dynamics. Some models propose that voids grow over time as matter streams away from underdense regions, becoming emptier as the universe evolves. The Boötes void exemplifies this process, serving as a natural laboratory for studying how matter moves and large-scale structures develop. The physical properties within the void also differentiate it from other regions. Its density is remarkably low. The matter within is so sparse that gravitational forces are weak. This allows light and radiation to pass through relatively unimpeded, providing clearer views of distant cosmic phenomena. Studying the void's interior enables scientists to analyze cosmic signals without the usual interference from dense galaxy clusters. For example, examining the light that passes through the void offers insights into cosmic background radiation and dark energy, which influence the universe's accelerated expansion. The Boötes void also plays a role in understanding dark matter. While dark matter constitutes most of the universe's mass, its distribution in voids like Boötes tests theories about its interaction with visible matter. The void's emptiness and how galaxies are arranged around it provide clues about dark matter's nature and behavior, helping refine models of cosmic evolution. In essence, the Boötes void is more than just a colossal space gap. It stands as a cosmic testament to the universe's complexity and grandeur, a vast, enigmatic expanse that pushes our ideas about matter, forces, and the universe's architecture. It serves as a reminder that much remains to be discovered in the universe's quiet corners, where fundamental secrets are often hidden in plain sight. The Boötes void is one of the most striking cosmic features, prompting questions about the universe's nature. It is a vast, nearly empty region in space stretching hundreds of millions of light-years. While seemingly simple, a large, empty space, its existence raises important questions when compared with current cosmological models about the universe's large-scale structure, making it a cosmic puzzle piece that challenges our understanding. Standard cosmological theories, especially the lambda-cold dark matter (LCDM) model, predict a universe woven from galaxy clusters, filaments, and voids. These voids are expected to be common, forming naturally from initial matter fluctuations after the Big Bang. The sizes and distributions of voids should follow certain statistical patterns. The Boötes void, approximately 150 million light-years across, aligns with some of these predictions. Its existence supports the idea that large-scale structure results from gravitational growth of early quantum fluctuations, amplified over billions of years. However, the size of the Boötes void also stretches the limits of what standard models consider typical. It is one of the largest known voids, and its extreme emptiness is difficult to reconcile fully. It contains far fewer galaxies than surrounding regions, raising questions about how such a colossal empty volume remains so devoid of matter. Slightly less dense initial fluctuations could explain parts of this, but the sheer size and emptiness challenge the expected limits of formation theories. Furthermore, cosmic voids like Boötes serve as natural laboratories for testing theories involving dark energy and modified gravity. Since voids are regions of low matter density, their dynamics are less affected by matter and more sensitive to the universe's overall acceleration. Observations of galaxy movements and evolution within and around these voids provide clues about dark energy. Whether it acts as a constant, as Einstein's cosmological constant suggests, or varies over space and time, void size and properties also facilitate testing for primordial non-Gaussianities, density fluctuations that deviate from a simple Gaussian distribution in the early universe. Detecting such deviations could uncover new physics beyond standard inflationary models. Because of its size and peculiarities, the Boötes void acts as a cosmic benchmark. Discrepancies between predictions and observations regarding the number, size, or distribution of voids can guide refinements in our theories. It confirms if our understanding of initial conditions is correct, or points toward missing fundamental physics. Some researchers suggest the void may reveal insights about the universe's overall shape and composition. Its vast emptiness hints at matter redistribution over cosmic time due to gravity and dark energy interactions. The observed matter clustering around the edges of the void supports the idea that gravity pulls matter into denser regions, leaving the interior relatively empty. Ultimately, the Boötes void functions as both confirmation and challenge. It supports the notion that the universe's structure arose from initial fluctuations amplified over time, yet it pushes the boundaries of our models. Its enormous size, emptiness, and existence compel astronomers to refine theories or explore new physics. The void demonstrates that even these empty spaces offer opportunities to deepen our understanding of the universe's fundamental workings. The formation of cosmic voids has long intrigued astronomers and cosmologists because these vast, seemingly empty regions challenge our understanding of the universe's large-scale structure. Several key theories explain how these enormous voids, like the Boötes void, come into existence. A widely accepted explanation centers on initial fluctuations in matter density in the early universe. Tiny variations right after the Big Bang set the stage for today's structure. In regions where the initial density was slightly lower, matter didn't accumulate as much. Over billions of years, these underdense areas expanded more rapidly than denser regions, creating large empty spaces, voids. The universe can be imagined as a cosmic sponge or foam, with dense clusters and filaments interconnected like foam bubbles. Gravity pulls matter together, amplifying density differences. Around voids, matter gravitates toward denser regions, leaving the voids emptier and larger over time. This gravitational flow pushes matter away from underdense regions, enlarging the voids as the universe evolves. Another prominent theory involves biased galaxy formation. Galaxies tend to form where initial densities exceed a threshold. Slightly less dense areas don't reach this threshold, resulting in fewer or no galaxies forming there. As galaxies and clusters develop in denser regions, less dense areas become naturally empty, forming the boundaries and interiors of voids. This model emphasizes the initial density fluctuations and how gravity magnifies them over cosmic history. Dark energy and the universe's accelerated expansion also influence void formation. As dark energy drives space to expand faster, underdense regions expand more rapidly than denser areas. This differential expansion causes voids to grow larger and more prominent over time. Essentially, the universe's expansion acts like a cosmic inflation mechanism, stretching these regions apart and making the void stand out against the cosmic web of galaxies and clusters. Some models, supported by computer simulations, suggest that interactions between dark matter and baryonic matter, combined with cosmic inflation shortly after the Big Bang, produce the large-scale web of filaments, nodes, and voids. Quantum fluctuations stretched during inflation seed this web-like structure, where matter clumps into dense nodes separated by vast empty regions. As the universe evolves, density contrasts become more pronounced, and voids grow larger and more defined. Overall, cosmic void formation results from the universe's initial conditions, driven by gravity, dark energy, and inflation physics. These processes work together, shaping the large-scale structure we observe today, with voids emerging naturally as vast, empty spaces created over billions of years. They serve as the counterpoints to galaxy clusters, completing the cosmic tapestry and revealing the intricate evolution of the universe's structure. Each theory offers insights into different mechanisms working in harmony to produce the grand, web-like cosmic landscape, an ongoing area of research that deepens our understanding of the universe's history and composition. Imagine the universe as a vast, three-dimensional spiderweb with filaments of galaxies and clusters interconnected across cosmic scales. These filaments are dense regions teeming with matter, stars, gas, dark matter, all gravitationally pulled together to form the cosmic highway system that stretches across the universe. Between these filaments lie enormous regions where matter is surprisingly sparse. These are the cosmic voids, some stretching over hundreds of millions of light years. So how does the rapid expansion of matter lead to the creation of these immense voids? To understand this, we need to think about the early universe, moments after the Big Bang. Back then, matter was nearly uniformly distributed, with tiny fluctuations in density, some regions slightly more dense, others somewhat less. As the universe expanded and cooled, these density differences began to amplify under the influence of gravity. In regions where matter was a little denser, gravity pulled in surrounding material, leading to even more accumulation of matter over time, forming the filaments and galaxy clusters we observe today. Conversely, areas with less matter became less dense as nearby matter was pulled into neighbouring structures. These underdense regions, where fewer galaxies and less matter exist, gradually expanded faster than the average due to the influence of dark energy, a mysterious force driving the acceleration of cosmic expansion. Think of it like a balloon covered with bubbles. The bubbles representing dense regions tend to grow, but slower compared to the spaces between them. Those gaps, initially tiny, expand more rapidly because they have less matter, a kind of cosmic escape from the dense zones. Over billions of years, these underdense regions grow into enormous empty spaces, cosmic voids. Mathematically, these processes are described by the laws of general relativity combined with the initial conditions set by the Big Bang and quantum fluctuations. When matter density is low, gravity's pull is weaker, allowing these regions to expand more freely and rapidly relative to denser regions. These underdense regions effectively push out the matter, leading to the evacuation of matter from the voids and the development of larger, emptier spaces over time. Another way to visualize it is through the concept of gravitational instability. Overdense regions attract more matter, becoming richer and denser over time, while underdense regions have less gravitational attraction, becoming increasingly empty. As these underdense regions expand faster, they become the vast voids we observe today. Dark energy enhances this effect because it accelerates the expansion of space itself, making the growth of voids even more pronounced. It's similar to how a rising bread dough creates bubbles. The dough expands, and the bubbles grow larger as space pushes outward. In the universe, the expansion is not limited to the surface of the dough, but occurs everywhere, causing the vast empty spaces to grow and stretch over cosmic time. In essence, the rapid expansion of matter, driven by the universe's initial conditions, gravity and dark energy, causes matter to congregate into dense filaments and clusters while simultaneously evacuating the less dense regions. These evacuated regions blossom into the colossal voids that carve the large-scale structure of the universe, making the cosmos a tapestry of shimmering galaxies interwoven with vast empty cavities. Dark matter and dark energy act as the unseen architects of the universe, shaping the grand tapestry in ways that are both mysterious and profound. To understand the formation and evolution of colossal structures like the Boötes void, we need to consider how these elusive components influence the cosmic landscape over billions of years. Dark matter, often called the scaffolding of the universe, is a form of matter that does not emit, absorb or reflect light. Though invisible to our telescopes, its gravitational pull is significant. In the early universe, tiny fluctuations in the density of dark matter caused matter to clump together, forming the vast filaments and clusters we observe today. These dense regions became the birthplaces of galaxies, clusters, and superclusters. However, where dark matter is less concentrated, weightier expanses of space, like the Boötes void, began to take shape. These enormous voids are the regions where the density of dark matter is particularly sparse. As matter was drawn into overdense regions, it effectively left behind vast empty spaces, voids, whose size grew over cosmic time. Imagine a universe where dark matter acts like a giant cosmic sponge, pulling matter into dense areas and leaving behind these gigantic empty regions. Over billions of years, these voids expanded and merged with neighbouring voids, becoming the enormous gaps we see today, some spanning hundreds of millions of light years. The growing emptiness within these regions isn't just a passive process. It's driven by the gravitational tug of dark matter, which pulls matter inward, evacuating the voids and making them even more empty. Dark energy, on the other hand, is the mysterious force that accelerates the expansion of the universe. This acceleration influences how voids grow and evolve. As the universe expands at an ever-increasing pace, the voids themselves stretch out, becoming larger and emptier over time. Think of dark energy as a kind of cosmic anti-gravity, pushing space apart and allowing voids to grow more rapidly than they could have in a universe without dark energy. This process doesn't just make voids bigger, it accentuates their underdensity, making them the vast, silent regions galactically devoid of matter that captivate astronomers. The interplay between dark matter and dark energy creates a dynamic environment where structures form and evolve. Dark matter's gravitational pull encourages the growth of overdense regions, while dark energy drives the expansion, enlarging voids. As a result, these voids become not only the largest structures, by volume, in the universe, but also natural laboratories for testing our understanding of fundamental physics. By studying how voids grow and change, scientists can glean insights into the nature of dark energy, probing whether it is a constant force or something more complex. In essence, dark matter provides the framework, the scaffolding that guides matter into dense clusters and leaves behind vast empty regions. Dark energy fuels the cosmic expansion, stretching these regions apart and magnifying their emptiness. Together, these two unseen forces sculpt the universe's most enormous and enigmatic features, allowing us to glimpse the underlying physics that govern the cosmos itself. The question of whether cosmic voids like the Boötes void are remnants of primordial fluctuations or the result of other processes touches on some of the deepest mysteries in cosmology. To understand this, we need to go back to moments immediately after the Big Bang, when the universe was a hot, dense, nearly uniform mixture of particles, energy, and radiation. Even in this uniformity, tiny quantum fluctuations existed, minute density variations that, over billions of years, grew into the large-scale structures we observe today: galaxies, clusters, and enormous voids. Primordial fluctuations are believed to be the seeds of all cosmic structure. These tiny variations were imprinted on space-time itself, recorded in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Temperature variations in the CMB directly correspond to early density differences. Regions slightly more dense gravitationally attracted matter, collapsing into galaxies and clusters, while less dense regions became the vast empty voids. In this framework, the largest voids, such as the Boötes void, could be primordial remnants. They are the footprints of initial fluctuations. Over cosmic timescales, gravity pulled matter into dense areas, causing underdense regions to expand and grow emptier, forming the voids we see today. This process can be likened to a sponge, the thick regions where matter accumulated and the gaps that opened up due to matter redistribution. However, their story isn't solely about primordial origins. Post-initial fluctuations also influence voids' development. Galaxy formation and evolution can affect the size and shape of these empty regions. Gravitational interactions and energetic feedback, like supernovae and active galactic nuclei, can push matter around, subtly modifying the cosmic web structure. Additionally, the universe's expansion, driven by dark energy, further amplifies voids' emptiness over time. Cosmic inflation, a rapid exponential expansion early in the universe's history, magnified quantum fluctuations, stretching them across vast scales and establishing the initial conditions for large-scale structure. Under this scenario, the enormous voids we observe are the grand-scale manifestations of those primordial ripples, expanded over billions of years into the empty gaps visible today. Some scientists suggest models where processes like supercluster mergers or dark matter distribution influence void formation beyond initial fluctuations. These mechanisms could explain variations in void size and shape, emphasizing that while initial seeds set the stage, ongoing matter-energy interactions continue to sculpt the universe's large-scale structure. Ultimately, the evidence supports the idea that cosmic voids like the Boötes void originate from a combination of initial quantum ripples and subsequent evolutionary processes. They are born from primordial fluctuations, then shaped and enlarged by cosmic expansion, gravity, and galaxy evolution. These vast emptinesses serve as cosmic relics, silent witnesses to the universe's birth and ongoing growth. They help us understand our origins and the fundamental forces shaping the cosmos. Simulations have become an invaluable tool in unraveling the mysteries of how cosmic voids, like the Boötes void, come into existence. These digital universes recreate the vast cosmic landscape, allowing astrophysicists to test various theories about the birth and evolution of these immense empty regions. By manipulating initial conditions and physical laws within these simulations, scientists can observe how different processes might lead to the formation of voids and compare those results with real observations. One of the fundamental theories about void formation is rooted in the idea that they emerge from the initial fluctuations in the density of matter in the early universe. In the primordial universe, tiny quantum fluctuations caused slight variations in density. Over billions of years, gravitational attraction caused matter to clump into galaxies, clusters, and filaments. leaving behind enormous empty spaces where matter was less concentrated, the birthplaces of voids. Simulations based on these initial conditions, often called lambda-cold dark matter models, show that as the universe evolves, these underdense regions expand faster than their denser surroundings, carving out the vast voids we observe today. In contrast, some alternative theories suggest that voids could be shaped significantly by dynamical processes such as mass flows or feedback effects from active galactic nuclei. To test these ideas, simulations incorporate complex physics like gas dynamics, supernova explosions, and black hole activity. If, in these models, voids form or expand more rapidly as a result of energetic outflows pushing matter away, then the simulated voids might differ in size, shape, or distribution compared to those formed solely by gravitational clustering. Comparing the properties of simulated voids under different physics helps researchers determine which processes dominate the formation and evolution of these regions. Further, some theories propose that voids are not just passive empty spaces, but might influence cosmic evolution through their effects on gravitational lensing or the propagation of cosmic microwave background light. To evaluate this, simulations embed the physics of light passing through a universe filled with varying densities, allowing scientists to predict signatures that could be observed by telescopes. If simulated voids produce lensing effects or temperature fluctuations consistent with observations, it lends weight to those particular theories. Simulations also enable scientists to explore the role of dark energy, a mysterious force driving the acceleration of cosmic expansion in void evolution. By adjusting the parameters governing dark energy within these models, researchers can see how the size and growth rate of voids change over time. If simulated voids under different dark energy scenarios match the vastness of the Boötes void, it suggests a profound connection between dark energy's properties and large-scale cosmic structures. By running numerous simulations with varying initial conditions, physics, and parameters, scientists can statistically compare the resulting voids with the real universe. The match or mismatch guides refinements in cosmological models and helps in choosing the most plausible theories. Through this iterative process, simulations become a cosmic laboratory where abstract theories about the universe's past, present, and future are tested and honed, leading us closer to understanding the true nature of colossal structures like the Boötes void. The density of matter inside the Boötes void is astonishingly sparse. When you consider the vast expanses of the universe filled with galaxies, gas, and dark matter, the Boötes void stands out as a staggering example of emptiness, a cosmic bubble almost devoid of matter. To put it into perspective, the average density of matter in the universe, including dark matter, is roughly 5 times 10 to the power of minus 21 grams per cubic centimetre. That sounds incredibly tiny, but the density inside the universe's general structure is still quite substantial compared to the void, which is essentially a giant, nearly perfect bubble of emptiness. Inside the Boötes void, the matter density drops to astonishingly low levels, around 10 to the power of minus 25 grams per cubic centimetre, or even less. To visualise how sparse that is, just compare it to the density of air here on Earth, which is about 1.2 grams per cubic centimetre. That means the matter inside the void is 1,000,000 times or even 1,000,000,000 times less dense than the air we breathe. It's almost as if this region of space is a vast cosmic hollow, where matter has been driven out or never gathered in significant quantities during the universe's evolution. Scientists have used galaxy surveys and redshift data to estimate these densities. They track the distribution of galaxies and intergalactic gas across billions of light years, and what they find is that the Boötes void contains fewer galaxies than typical regions of the universe. In some sections, there are practically none. The galaxies that are observed within the edge of the void tend to cluster along the filaments and walls that define its boundary. But inside this enormous bubble, galaxies are few and far between, separated by immense distances, sometimes hundreds of millions of light years. The scarcity of matter inside the Boötes void isn't just accidental. It's a consequence of the early universe's primordial fluctuations. Tiny differences in the density of the nascent cosmos, amplified over billions of years by gravitational attraction, led to the formation of dense regions like galaxy clusters and the enormous emptiness of vast voids. Over cosmic time, gravity pulled matter into filaments, sheets, and clusters, leaving behind these immense regions of near-total emptiness. The dynamics of dark energy, which drives the universe's accelerated expansion, also play a role in stretching these voids apart, further diluting their matter content. Given the size of the Boötes void, some estimates place it at about 150 million light-years across. Its extraordinary emptiness is a testament to the complex, chaotic processes that have shaped our universe. It serves as a natural laboratory for understanding cosmic evolution, dark matter and dark energy. Studying these regions can help answer profound questions about how matter behaves on the larger scales and how the universe's large-scale structure emerges from the subtle initial conditions set shortly after the Big Bang. The emptiness of the Boötes void isn't just a feature of space, it's a window into the universe's deepest, most fundamental workings. Bordering the immense emptiness of the Boötes void are galaxies that seem to have arrived at the edge of this cosmic chasm, like travellers standing on the brink of a vast silent plain. These galaxies are often irregular in shape, somewhat scattered, and less densely packed than those in clusters teeming with hundreds or thousands of inhabitants. They're mostly faint dwarf galaxies, dim and elusive, often dwarfed by their brighter, more luminous counterparts that grace the denser regions around the void. It's as if they're timid settlers, naturally sparse and spread out, making their presence just noticeable against the vast backdrop of nothingness. Within the boundaries of the void itself, the matter takes on a still more subdued character. Instead of bustling clusters of star giants or tightly woven chains of galaxies, the interior is primarily filled with the sparse glow of isolated galaxies whose light has taken billions of years to reach us. Some of these galaxies are bathed in a gentle hue, their stars flickering quietly amidst a quiet darkness. Many are small, gas-rich systems where star formation continues at a slow pace, their gas clouds lingering like faint whispers of potential. These galaxies tend to be less evolved, sometimes irregular in shape, lacking the grand spirals or stately ellipticals seen elsewhere in more crowded cosmic neighbourhoods. The matter inside the void isn't confined solely to luminous galaxies. Invisible to the naked eye but crucial to the universe's tapestry is the dark matter. While dark matter cannot be seen directly, its existence inferred through gravitational effects, its role is vital in shaping the structure of the universe. In the regions bordering the Boötes void, dark matter clumps form the scaffolding upon which visible matter gathers, creating the filaments and walls that define the edges of these enormous voids. These dark matter concentrations serve as gravitational anchors, drawing in gas and galaxies, forming the near boundaries of the void and supporting the larger cosmic web. Straying into the void itself, the matter becomes even more diffuse. Hydrogen gas, the universe's most abundant element, is scattered thinly across the expanse. This diffuse gas, sometimes called the intergalactic medium, exists at near vacuum levels of density, giving the void a ghostly, transparent quality when observed through specialized instruments. Occasionally, faint clouds of neutral hydrogen can be detected glowing faintly in Lyman alpha emissions, revealing the presence of matter stretched over millions of light-years. These gaseous pockets are often remnants of the early universe, slowly continuing their silent dance through cosmic time. The matter within and around the Boötes void illustrates a fascinating contrast. Order and chaos, brightness and darkness, densely packed galaxies and near-perfect emptiness coexisting in a vast cosmic symphony. The galaxies bordering the void are witnesses to this immense structure, their distributions and compositions offering clues about how large-scale cosmic processes unfold. They remind us of the delicate balance, gravity pulling matter together while the universe's expansion pushes it apart, shaping these colossal voids that define the universe's expansive architecture. It's a testament to the universe's grandeur, a reminder of how something as seemingly simple as emptiness can serve as the foundation for the universe's most awe-inspiring structures. Scientists use various advanced techniques to understand how galaxies are distributed around the Boötes void, exploring how these vast empty regions influence the universe's large-scale structure. One primary method involves large-scale sky surveys, which map the positions and velocities of millions of galaxies. Projects like the Sloan Digital Sky Survey, SDSS, have created detailed three-dimensional maps by cataloguing numerous galaxies across large sky regions. These maps reveal the cosmic web of filaments, clusters, and voids, illustrating how galaxies are arranged around these enormous gaps. In these surveys, astronomers measure galaxy redshifts to determine their distances, helping to build a three-dimensional map of galaxy distribution. Analysing this data shows how galaxies cluster or disperse relative to voids. Scientists identify the boundaries of voids like the Boötes void, and examine galaxy densities outside these regions. This analysis reveals the density contrasts, how sparse the void is compared to surrounding areas, and the transition's sharpness or smoothness from emptiness to denser matter. Another crucial technique involves gravitational lensing. Massive objects like galaxy clusters bend light from distant galaxies, and the resulting distortions reveal the distribution of dark matter, the invisible scaffold that influences galaxy positioning and evolution. Since dark matter can't be observed directly, gravitational lensing allows scientists to map its distribution around voids. Light passing through regions bordering a void shows subtle distortions, providing clues about the underlying mass distribution influencing galaxy arrangements. Studies also focus on the velocities of galaxies near the void's edges using spectroscopic measurements. By observing Doppler shifts in their light, researchers assess whether galaxies are moving away from the void's center, indicating they are being pulled outward by surrounding dense regions, or falling into neighboring filaments and clusters. These velocity patterns encase information about gravitational influences, mainly dark matter and dark energy, shaping the growth of voids and the surrounding structures. Cosmologists depend heavily on computer simulations incorporating physics, dark matter, and dark energy. Based on initial conditions derived from measurements like the cosmic microwave background, they recreate virtual universes, observing how large-scale structures evolve over billions of years. Comparing these simulations with actual galaxy observations around the Boötes void helps test models of cosmic evolution and the forces sculpting the cosmos. Statistical tools, especially correlation functions such as the two-point correlation function, are used to analyze galaxy distributions. These functions measure how galaxy positions relate at different scales, revealing characteristic clustering or emptiness patterns. Such measures help determine the scales at which matter tends to cluster or form voids, shedding light on gravitational processes that shape the universe's large-scale structure and the roles of matter, and dark energy in these dynamics. All these methods together produce a comprehensive understanding of galaxy behavior around the Boötes void, revealing how galaxies cluster, flow, and interact. They transform the universe's silent expanses into a dynamic laboratory, showing that even the emptiest regions contain valuable information about cosmic history, composition, and future evolution. Studying the distribution of galaxies around voids not only enriches knowledge of the universe's structure, but also illuminates fundamental forces at work, deepening our understanding of the cosmos. Inside the Boötes void, conditions are remarkably different from the bustling regions filled with galaxies and clusters. This vast expanse of emptiness, spanning hundreds of millions of light-years, hosts a sparse and almost surreal environment that offers a unique window into the universe's fundamental workings. The temperature within the void is, unsurprisingly, much cooler than in denser regions of space. Unlike galaxy clusters, where intergalactic gas is heated through gravitational interactions and shock waves to millions of degrees Kelvin, the gas floating through the void remains extremely tenuous and cold, probably just a few tens of thousands of Kelvin at most. This cooling stems from the lack of nearby massive objects whose gravity and energetic processes can heat the surrounding medium. Instead, the gas here is mostly residual, left over from the universe's early days, slowly cooling as it expands into the emptiness. Dark matter, which makes up about 85% of all matter in the universe, also occupies these voids, but in a dramatically diffuse state. While the universe's large-scale structure is a cosmic web, woven from filaments rich in dark matter and galaxies, the voids themselves are marked by an almost complete absence of this mysterious substance. Yet dark matter isn't entirely absent, it's just incredibly underdense here. Simulations suggest that dark matter's distribution in the void is highly sparse, reflecting the dark matter filaments and halos that have been pushed outwards during the universe's expansion. These regions contain tiny clumps or halos of dark matter, too small to host galaxies, but their presence influences the gravitational landscape, subtly shaping the outskirts of the void structure. Gas conditions mirror this scarcity. The intergalactic medium within the Boötes void is incredibly rarefied, with densities hundreds of times lower than in denser regions. The gas there is primarily hydrogen and helium, the primordial elements formed in the moments after the Big Bang, still lingering in a diffuse state. This gas is so sparse that when astronomers look through the void with powerful telescopes, they see it as almost nothing, a faint, almost invisible filamentary web that's been stretched and thinned by cosmic expansion. Despite this extreme emptiness, this gas is not entirely absent. It plays a subtle role in the cosmic landscape, absorbing some light from distant quasars and creating delicate absorption lines that reveal its presence. Interestingly, the interaction of these gases with the ultraviolet background radiation permeating the universe keeps some of the hydrogen ionized, preventing it from collapsing into stars or dense clouds. But without the gravitational pull of dense matter, this gas remains diffuse, with temperatures maintained by the balance between radiation heating and adiabatic cooling from expansion. Overall, the conditions inside the Boötes void tell a story of cosmic emptiness and quietude. Temperatures are low, dark matter is sparse but influential in shaping the edges, and the gas, although incredibly thin, reveals subtle clues about the universe's early moments and ongoing evolution. Exploring these conditions helps scientists understand not just what the universe was like in its dark, tangled past, but also how it continues to grow and evolve in the vast expanses of near-emptiness that stretch between the luminous nodes of galaxy clusters. When we peer into the depths of the Boötes void, what truly stands out is how its composition sharply contrasts with what we see in the universe at large. The cosmic average is a bustling, lively place filled with galaxies, stars, gas, and dark matter, each weaving together into the intricate cosmic web. But within this colossal emptiness, the scene is significantly different. In most regions of the universe, baryonic matter, comprising everything from glowing stars to vast clouds of gas, is spread relatively evenly when you move across large scales. This matter forms the luminous structures we see in telescopes, making up a little more than 5% of the universe's total energy budget. Dark matter, the elusive substance that exerts gravitational pull and scaffolds galaxy formation, accounts for about 25%. The remaining 70% of the universe's energy density is attributed to dark energy, driving its accelerated expansion. Now, in the Boötes void, the story is quite remarkable. Instead of the familiar smattering of galaxies and luminous matter, the void's contents are sparse, so sparse in fact that galaxies are few and far between. If you were to venture into its centre, the density of matter could be just a fraction of the average cosmic density, sometimes less than 10% of what we typically observe. This means that compared with the universe's plush, filled-in regions, the void is a vast, almost empty expanse. But how does this emptiness manifest in the matter composition? Surprisingly, the proportion of dark matter still lingers within the void, but because there is so little total matter present, the gravitational influence it exerts is minimal. Essentially, dark matter, while still present, is spread thin and contributes less to shaping the void's structure compared to denser regions. The sparse galactic populations that do dwell here are typically smaller and less luminous, often dwarf galaxies or faint diffuse collections of gas. Additionally, the gas that does exist in the voids is much less dense and cooler than in the cosmic web's filaments. High-energy processes, like supernova explosions and active galactic nuclei, are rarer in these regions, leading to fewer sources of heating or ionization. That leaves the intergalactic medium within the void largely composed of thin, cold hydrogen gas, so diffused that it hardly emits or absorbs electromagnetic radiation, detectable with ordinary telescopes. When scientists look for the faint glow of the warm, hot intergalactic medium within the void, it's almost like searching for a whisper in a thunderstorm, quiet and elusive. This stark contrast in composition makes the Boötes void a kind of natural laboratory. Its relative emptiness provides a pristine environment to test models of cosmic evolution, dark matter distribution, and the influence of dark energy. Because there's so little matter to interfere, the gravitational effects are minimal, helping scientists isolate the fundamental physics shaping our universe on the largest scales. Yet, despite its emptiness, the Boötes void isn't entirely devoid of matter or structure. Tiny, faint galaxies and pockets of gas do exist within its boundaries, serving as vital clues. They remind us that even the most immense emptiness in space isn't truly empty. It's just a region where matter is incredibly sparse, compared to the bustling, luminous universe we often imagine. The existence of colossal voids like the Boötes void has profound implications for our understanding of cosmic evolution. These enormous stretches of emptiness, spanning hundreds of millions of light years, aren't just empty spaces. They serve as cosmic laboratories that challenge and refine our theories about how the universe came to be and how it continues to change. One of the key insights that voids provide is about the large-scale structure of the universe itself. According to the current cosmological model, shortly after the Big Bang, the universe was nearly uniform, with tiny fluctuations in density. Over billions of years, gravity amplified these minute irregularities, causing matter to clump together into galaxies and galaxy clusters, while vast regions remained comparatively empty, evolving into the voids we observe today. The striking size and distribution of these voids support the idea that the universe's structure grew through gravitational instability, reinforcing our understanding of the universe's initial conditions and the role of dark matter in shaping these structures. Void regions also shed light on the mysterious influence of dark energy. As the universe expands at an accelerating rate, an observation that earned the 2011 Nobel Prize in Physics, understanding what drives this acceleration becomes critical. Voids, being less dense, expand faster than denser areas, making them sensitive indicators of the universe's overall expansion dynamics. By studying the growth and evolution of voids over cosmic time, scientists gain valuable clues about the properties of dark energy. Are its effects constant, or do they change over time? The way voids evolve helps to answer these questions, providing indirect but powerful probes into one of the universe's greatest mysteries. Furthermore, voids influence the way structures form and evolve. They act as cosmic backdrops against which galaxies and clusters evolve. Interestingly, some galaxies found within or near voids exhibit peculiar properties. They tend to be less massive, with different star formation rates compared to galaxies in denser regions. This contrast reveals how environment plays a role in galaxy evolution, and studying these isolated galaxies helps scientists test models of how matter assembles over time. Void regions also refine our understanding of fundamental physics. Because these areas are so sparsely populated, they are less affected by complex astrophysical processes such as supernova explosions, interactions between galaxies, or the influence of active galactic nuclei. This relative simplicity makes voids ideal for testing theories of gravity and the behavior of dark matter on large scales. Some cosmologists explore whether modifications to Einstein's theory of general relativity could better explain the universe's accelerating expansion. Voids serve as crucial testing grounds for these alternative hypotheses. Finally, the study of voids opens doors to exploring new physics. If observations of these empty regions reveal unexpected phenomena or deviations from predicted models, scientists might be forced to rethink our fundamental assumptions about the fabric of space, the nature of dark matter, or even the properties of gravity itself. In essence, the immense voids, like the Boötes void, aren't just vast empty gaps. They are cosmic beacons that illuminate the underlying principles governing the universe's past, present, and future. They help us piece together the story of cosmic evolution, from the aftermath of the Big Bang to the accelerating universe we observe today, pushing the boundaries of our understanding to new and exciting horizons. The existence of such an enormous void as the Boötes void sparks questions about our universe's structure and whether current cosmological models can fully explain these colossal gaps in matter. For years, scientists have relied on the lambda-CDM model, the standard cosmological framework which describes the universe's evolution from its hot, dense beginnings to its current state. This model incorporates dark energy, dark matter, and ordinary matter, portraying a universe where structures form from tiny initial fluctuations amplified over billions of years through gravity. Within this framework, the large-scale structure emerges as a cosmic web, a complex network of galaxy filaments, clusters, and vast empty regions called voids. Voids are not merely empty spaces, but regions where matter density is significantly lower than the cosmic average. They result naturally from the universe's structure formation process, as gravitational tug-of-war pulls matter into dense regions while leaving others relatively empty. Cosmological simulations support this, indicating that voids develop and grow over cosmic time, fitting within the standard model's predictions. Nevertheless, the size and emptiness of the Boötes void raise intriguing questions. Spanning approximately 150 million light-years, it is huge enough to stretch some model predictions. Can such a massive void form within our current understanding? Is it an anomaly, or does it reveal gaps in our knowledge? These questions have led to debates among cosmologists. Some suggest the void's size might be a statistical fluke, an unlikely but possible occurrence within the probabilistic nature of the model. Others argue that the very existence of such a supervoid may point to the need for refining our models or re-examining assumptions, such as the uniformity of dark energy or the properties of dark matter. Advanced computer simulations show voids can grow and coalesce over cosmic time, producing larger empty regions. While the Boötes void is atypically large, simulations suggest it falls within the realm of possibility for the standard cosmological framework. Still, the universe remains a vast, surprising place. Each large void offers a chance to test our understanding of structure formation and evolution, reminding scientists that many mysteries remain, especially regarding dark energy and dark matter, which influence the universe's expansion and matter clustering. Some researchers speculate that supervoids like Boötes could influence local measurements of the universe's expansion rate. Might they bias assessments of cosmic acceleration? Could large voids help explain discrepancies in the Hubble constant, the current rate of cosmic expansion? These questions highlight the importance of studying large voids. They may contain clues to new physics or simply be rare, natural features of the universe's grand structure. So, does the Boötes void challenge current models? It pushes their limits but does not necessarily overthrow them. Instead, it provides a natural laboratory on a cosmic scale, prompting scientists to refine theories, deepen their understanding, and possibly uncover new physics beyond what's currently known. The existence of vast voids exemplifies the universe's complexity and the ongoing quest to comprehend its full nature, showing that even the biggest gaps in matter are valuable opportunities to learn. The immense emptiness of the Boötes void isn't just a striking visual feature of the universe's architecture, it plays a significant role in shaping the gravitational landscape around it and influences how galaxies move through space. Because gravity is the force that governs the motion of objects on cosmic scales, the sheer absence of matter within such a vast region leads to unique gravitational effects that ripple outward, affecting the neighbouring cosmic structures. Imagine galaxies near the edge of the void. They sit in a kind of cosmic tug-of-war, where the density of matter influences their journeys through space. Within the dense regions of the universe, clusters of galaxies and filaments, gravity pulls galaxies toward each other, creating the intricate web-like pattern we observe. But when galaxies are close to a void like Boötes, they experience a different kind of gravitational influence. Instead of being pulled inward by the surrounding matter, they are subtly pushed away from the emptiness. This is because gravitational attraction is strongest where matter is concentrated, and with so little matter within the void itself, the net effect on galaxies near its boundary is a slight repulsive influence from the contrast between the dense regions and the emptiness of the void. As a result, galaxies on the outskirts of the Boötes void tend to drift away from it, moving faster than they would if the void weren't there. This outward push isn't because there is a force actively ejecting them, but rather because they are responding to the gravity imbalance, being pulled more strongly toward the denser regions surrounding the void. Over cosmic timescales, this effect causes galaxies near the edges of the void to accelerate outward, contributing to the large-scale flow patterns observed in the universe. This phenomenon, often described as a sort of gravitational expulsion, influences the large-scale flow of cosmic structures. These galaxy motions aren't random. They reflect the underlying distribution of matter and the empty spaces that carve through it. The gravitational pull of dense regions, combined with the relative emptiness of regions like the Boötes void, creates a cosmic landscape where galaxies are gently but persistently guided away from the voids and toward regions of higher matter density. The influence of voids extends beyond just gravitational motions. They help shape the evolution of the large-scale structure by acting as cosmic scaffolding, areas of low matter density that allow galaxies to cluster and evolve in specific patterns. Because the galaxies respond to the gravity governed by dark matter, these voids provide scientists with clues about the unseen mass that influences the universe's dynamics. By studying how galaxies move around these voids, researchers gain insight into the distribution of dark matter and the influence of dark energy in shaping the universe's expansion. In essence, the Boötes void acts as a giant cosmic basin, sculpting the dance of galaxies at its periphery. Its emptiness pulls at their motions, nudging them outward, and contributing to the grand cosmic flow that continuously reshapes what we observe in the universe. Understanding these subtle gravitational influences helps scientists peel back the layers of cosmic history, revealing how the universe's vast and seemingly empty regions are anything but insignificant. They are fundamental to the story of cosmic evolution. Studying the Boötes void offers an exceptional opportunity to refine our measurements of dark energy, advancing our understanding of the universe's most mysterious force driving its accelerated expansion. Although seemingly just an enormous empty region of space, the void's unique properties and scale make it a powerful natural laboratory for cosmological investigation. Its vast size, spanning hundreds of millions of light-years, allows scientists to observe the large-scale structure of the universe with minimal interference from matter-dense regions like galaxy clusters, providing clearer insights into how dark energy influences cosmic evolution. The key reason the Boötes void is valuable for studying dark energy lies in its effect on galaxy distributions and motions. Near the edges of the void, the dynamics of galaxies, their positions, velocities, and clustering patterns, encode information about the universe's expansion rate over cosmic time. As galaxies move outwards from the void's center, their velocities are influenced by the interplay of gravity and dark energy. By precisely measuring these velocities using redshift surveys and mapping galaxy positions, researchers can compare the observed large-scale flows against predictions from cosmological models that incorporate different dark energy properties. In particular, the gravitational influence of matter within and surrounding the void helps to isolate the effects of dark energy on the universe's expansion. Since the interior of the void is underdense, its gravitational pull is weaker than denser regions, resulting in less gravitational hindrance to the acceleration of the universe. This relative emptiness acts as a cosmic quiet zone, where the effects of dark energy can be observed with minimal contamination from matter's gravitational pull. As a result, measurements of galaxy velocities near the void's boundaries are less affected by local gravitational complexities, providing a cleaner signal from which to infer the properties of dark energy. Moreover, because the void's size correlates with the overall expansion history, studying the void's growth over cosmic time can reveal how the influence of dark energy has evolved. Observing how the void's shape and extent change across different epochs enables scientists to place constraints on whether dark energy behaves like a cosmological constant, remaining steady over time, or whether it varies dynamically. These insights are crucial because they help differentiate between competing theories: a static versus a dynamic dark energy model. In addition, the integration of void studies with other cosmological observations, such as supernova distance measurements, baryon acoustic oscillations, and the cosmic microwave background, improves the robustness of dark energy constraints. Combining these diverse datasets reduces uncertainties, leading to tighter bounds on dark energy parameters. As observational techniques improve, particularly with upcoming surveys like DZ or Euclid, the accuracy of galaxy redshift measurements near voids will increase, further sharpening our understanding. Ultimately, the Boötes void's vast emptiness and well-characterized structure make it an invaluable tool for probing the large-scale effects of dark energy. Its measurements help refine the fundamental parameters of cosmic acceleration, bringing us closer to resolving one of modern cosmology's biggest mysteries. In essence, the void is not just an absence of galaxies, it's a cosmic laboratory helping us unveil the forces shaping our universe's destiny. The vastness of the Boötes void offers a striking glimpse into one of the fundamental principles of cosmology, that, on the largest scales, the universe is both uniform and isotropic. These concepts are central to modern cosmology. Uniformity suggests that matter and energy are roughly evenly distributed at scales of hundreds of millions of light-years, while isotropy means the universe appears the same in every direction. Together they underpin the cosmological principle, which states that the universe, on large scales, is homogeneous and isotropic. When examining the Boötes void, we test these assumptions. Voids are not just empty spaces. They are the largest known structures, spanning hundreds of millions of light-years. If the universe is truly uniform and isotropic, these vast gaps should look similar when viewed from different vantage points or directions. Their existence and characteristics inform us whether these principles hold exactly or only approximately. The Boötes void presents a challenge beyond mere emptiness. Its size, shape, and distribution test whether the universe is truly the same everywhere, or if there are preferred directions or regions deviating from uniformity. Such colossal voids suggest matter is not perfectly evenly spread, but tends to cluster, leaving behind these enormous gaps. This pattern of lumpy matter distribution reflects gravitational forces and the initial fluctuations in density that seeded structure formation. Yet, despite these dramatic voids, the universe appears remarkably consistent at large scales. Galaxy surveys reveal a cosmic web, filaments, clusters, and voids arranged in repeating, scalable patterns that support the idea of an underlying uniformity. Voids like Boötes do not contradict this. They highlight the universe's large-scale structure, cell-like regions of emptiness separated by dense filaments of galaxy clusters. Observations of the cosmic microwave background, CMB, reinforce this view. The CMB is incredibly uniform with only tiny fluctuations, suggesting that shortly after the Big Bang the universe was nearly uniform. The large voids we see today, like Boötes, are natural outcomes of the growth of these initial fluctuations under gravity's influence over billions of years. These voids are, in essence, the universe's way of echoing its early uniform state after cosmic evolution. The existence of the Boötes void reassures us that the universe's large-scale structure reflects a delicate balance, a cosmic tapestry woven from initial uniformity, shaped by gravitational instability. It is characterized by dense clusters and enormous empty regions. Though the universe exhibits remarkable variation locally and regionally, the grand design remains consistent. This supports the notion that the universe, on the largest scales, is both remarkably uniform and isotropic. This intricate dance of randomness and order continues to inspire our understanding of the cosmos. Large voids like Boötes reveal that the universe's structure results from initial uniformity, molded by gravity, producing a pattern of dense regions and vast emptiness. They lead us to a deeper appreciation of the universe's grand design, which, despite apparent small-scale chaos, maintains a remarkable large-scale regularity. Future missions and powerful telescopes are set to revolutionize our understanding of cosmic voids, shedding new light on these enormous, seemingly empty regions of the universe. As technology advances, astronomers are preparing to explore the voids with unprecedented detail, unlocking secrets about the universe's structure, its history, and the fundamental physics that govern it. One of the most anticipated projects is the Vera C. Rubin Observatory, which will soon begin full operations. With its wide-field camera and rapid survey capabilities, it will capture vast amounts of data about billions of galaxies. By mapping galaxy distribution across large regions of space, scientists can pinpoint the shapes and sizes of cosmic voids more precisely. Its imaging will help analyze how voids evolve over time, providing clues about dark energy, gravity, and cosmic expansion. Tracking subtle changes in galaxy distribution will deepen understanding of the large-scale cosmic web and voids' roles within it. Complementing this is the Euclid mission by the European Space Agency, primarily aimed at studying dark energy and dark matter. Euclid's high-precision measurements of galaxy clustering and weak gravitational lensing will also be invaluable for studying cosmic voids. By examining how light from distant galaxies is bent passing through different regions, Euclid will reveal the matter distribution, including dark matter, around voids, helping scientists understand their formation and growth. Its deep space imaging will also enable detection of low-density regions that are hard to observe with existing telescopes. The Nancy Grace Roman Space Telescope will also contribute significantly. Its advanced infrared capabilities will enable detailed observations of distant galaxies and the cosmic web's filaments and voids. Infrared observations allow it to peer through cosmic dust that often obscures parts of the universe, providing a clearer picture of the large-scale structure. This will facilitate detecting voids at earlier stages, offering insights into their expansion and evolution over billions of years. Ground-based observatories play a crucial role too. The Square Kilometre Array, one of the largest radio telescopes under construction, promises to map large-scale structures with extraordinary sensitivity. Its ability to detect hydrogen signals across cosmic time will help trace matter distribution and reveal the subtle boundaries and internal structures of voids. This can test theories about dark energy's role in accelerating expansion and how voids influence galaxy formation. All these instruments and missions form a synergistic approach to studying cosmic voids. By combining optical, infrared, and radio observations, scientists will develop a more comprehensive understanding of these vast regions of emptiness. As data from these advanced tools accumulates, the mysterious voids will become clearer, revealing their vital role in the cosmic tapestry. This will bring us closer to understanding the universe's deepest secrets and the fundamental physics driving its expansion and evolution. Advances in technology continually reshape our capacity to detect, analyze, and understand cosmic voids like the Boötes void, enabling astronomers to probe deeper into these vast, seemingly empty regions of space. Currently, telescopes operating across multiple wavelengths — radio, infrared, visible, and X-ray — allow us to chart galaxies, galaxy clusters, and large-scale structures, revealing the universe's complex architecture. Future technological developments are poised to dramatically enhance these capabilities, offering unprecedented insights into the nature and evolution of voids. A major leap involves deploying next-generation telescopes both on the ground and in space. Ground-based observatories like the Vera C. Rubin Observatory will utilize large, wide-field optical surveys to generate detailed, expansive 3D maps of the universe. Their large apertures will capture faint light from distant galaxies, allowing more precise measurements of galaxy distribution and density fluctuations. Space telescopes such as the Euclid mission and the Nancy Grace Roman Space Telescope will extend our observational reach, capturing high-resolution images in infrared and visible wavelengths. These instruments will better delineate the boundaries of cosmic voids, revealing internal structures, subtle subvoids, and filamentary connections to surrounding matter. The combination of larger data sets from these telescopes necessitates advanced computational tools. Machine learning algorithms and artificial intelligence will process colossal data sets efficiently, identifying voids more precisely than traditional methods. These algorithms can differentiate between slight underdensities and true void regions, classify void types, and track their evolution over cosmic time. AI-driven simulations will generate models of void formation, enabling scientists to compare simulated structures with observations, refining our understanding of gravitational dynamics, dark matter interactions, and dark energy's role. Detecting the universe's dark components indirectly has become a promising approach. Gravitational lensing, where massive objects bend traveling light, can map dark matter within and around voids. Advances in lensing techniques, higher resolution detectors, and extensive surveys will reveal dark matter structures underlying visible galaxy distributions. This insight enhances models of void formation and evolution, illustrating how the cosmic web influences galaxy motion and clustering, and clarifies the role of dark matter in shaping large-scale structures. Radio astronomy breakthroughs, particularly 21 centimeter line observations of neutral hydrogen, will revolutionize void studies. These faint signals penetrate cosmic dust, revealing the distribution of diffuse hydrogen within the emptiest regions of space. Clarifying whether voids contain primordial gas reservoirs, these studies illuminate processes like matter accretion, gas dynamics, and the intergalactic filaments connecting structures. This helps determine the true emptiness of voids and their role in cosmic evolution. Emerging space-based initiatives, including nanosatellite constellations and dedicated cosmic survey satellites, will enable continuous, real-time sky monitoring, free from atmospheric interference. These missions will vastly expand observational capabilities, allowing detailed mapping of large-scale structures and revealing more about the role of voids in cosmic history. Such data will improve understanding of how voids influence galaxy formation and universe evolution. Each technological stride, whether through advanced telescopes, innovative data analysis, or novel observation methods, brings us closer to understanding the nature of cosmic voids. They will help decode how voids form, their influence on cosmic evolution, and their role within the larger cosmic web. Ultimately, these innovations will deepen our grasp of the universe's fundamental architecture, uncovering secrets held within the largest holes in the cosmos. Despite significant progress in understanding the Boötes void, researchers still face major challenges in fully uncovering its nature. One primary obstacle is its vastness and emptiness. The void spans about 1 billion light-years, making comprehensive observation and sampling extremely difficult. Current telescopes and surveys are limited in probing such enormous, nearly empty regions. Observations mainly focus on the boundaries or walls where galaxies are more concentrated, leaving the interior largely unexplored. Consequently, much of what is known about the deep interior is inferred indirectly from boundary regions rather than through direct observation. Detecting faint or distant objects inside the void poses another challenge. Many potential galaxies there are dim, making them hard to observe against the cosmic background. Existing instruments, despite their strength, struggle with the low surface brightness of such objects. This likely results in underestimating the number of galaxies within the void and missing exotic or primordial objects, which skews our understanding of its composition and role in cosmic evolution. Cosmic variance, an observational bias, further complicates efforts to analyze the void's properties. Since we observe only one universe, and the Boötes void represents just a small part of the cosmic web, it's difficult to determine whether its features are typical or unique. Variations across different regions of the universe can be significant, especially in large-scale structures. This variability makes it challenging to generalize findings from the Boötes void to broader cosmological models, adding uncertainty to theories about its formation and evolution. Limitations of current computer simulations also hinder progress. Cosmologists develop sophisticated models to emulate the universe's growth and the development of voids, but these simulations are computationally demanding. Replicating something as vast as the Boötes void requires enormous processing power and high-resolution data, which are not always accessible. Also, models depend on poorly constrained parameters related to dark matter and dark energy, leading to uncertainties in predictions regarding void formation and properties. Understanding the influence of dark energy on such large structures remains another major hurdle. Dark energy drives cosmic acceleration, yet its precise nature and effects are poorly understood. This lack of understanding limits our ability to predict how voids like Boötes will evolve over cosmic time. It also hampers assessments of whether these voids could influence galaxy formation or impact the large-scale formation of structures in the universe. Technological barriers are ongoing as well. Although telescope sensitivity and survey scope have improved, they still fall short of fully probing these enormous sparse regions. Upcoming projects like the Vera C. Rubin Observatory promise better observations, but much work remains to unveil the interior of the universe's largest voids. Until technological advances fully catch up, our knowledge of the Boötes void remains incomplete, a mixture of known facts and elusive mysteries. The vastness, faintness of objects, observational biases, computational limitations, dark energy uncertainties, and technological challenges collectively shape the current landscape of void studies. These obstacles prevent a complete understanding of the Boötes void and inspired ongoing efforts to push the boundaries of observation, simulation, and theory. Overcoming them is essential for developing a comprehensive picture of how such colossal structures form, evolve, and influence the universe at large. Future research promises to dramatically advance our understanding of the universe's grand design. As technology improves and new observational methods develop, scientists will peer deeper into the cosmos, discovering previously unseen structures and phenomena. Each breakthrough could reshape the cosmic map, adding complexity and nuance to the large-scale structure that spans the universe. One of the most exciting prospects is the enhancement of galaxy surveys. Projects like the Dark Energy Spectroscopic Instrument are already mapping millions of galaxies with unprecedented precision. As surveys expand, they'll provide a clearer picture of the cosmic web's intricate network of filaments and voids. Better data will refine models of how these structures form and evolve over billions of years, possibly challenging current ideas about the roles of dark matter and dark energy in shaping the universe. Advances in computational power enable detailed simulations of cosmic evolution. These virtual experiments test theories about the origin and development of large-scale structures. As models become more sophisticated, they could reveal unexpected phenomena or subtle effects previously overlooked. For example, researchers might discover new mechanisms behind the growth and interaction of voids with surrounding filaments, or detect subtle patterns in galaxy distributions indicating unknown physical processes. Another frontier involves the study of cosmic voids themselves. As more data is gathered, scientists will better understand how voids like the Boötes void form, expand, and influence their environment. Future research may show that voids are not simply empty gaps, but active regions impacting galaxy formation and dark energy's influence on universe expansion. These insights could lead to a reassessment of the significance of these vast regions and their role within the cosmic web. The integration of multi-messenger astronomy will add new dimensions to our understanding. Gravitational wave detections and neutrino observations can provide clues about the universe's early history and the behavior of matter and energy under extreme conditions. Combining these signals with large-scale structure data may reveal links between phenomena at the smallest scales, like black hole mergers, and the universe's largest features, such as cosmic voids and filaments. Perhaps most revolutionary is the potential discovery of new physics, questioning whether current models are complete. Future research might unveil phenomena that challenge Einstein's theories, prompting the development of entirely new frameworks for understanding gravity, space, and time. This could usher in an era where the universe's structure is seen as dynamic and interconnected with previously unimagined dimensions or forces. Each step forward will refine our perception of the universe, revealing greater detail and depth. The seemingly empty voids may prove to be key players in cosmic evolution, holding secrets that could shed light on the very nature of reality. As these mysteries unravel, the universe's grand architecture will come into sharper focus, exposing its size, complexity, and profound interconnectedness, governed by fundamental laws. Many mysteries about the Boötes void and cosmic voids remain, inviting further exploration. A major question concerns their origins. While we know they formed from initial density